We build our cities on grid systems and lay our roads in straight lines. From walking down a hallway to driving on a highway, human life is engineered almost entirely around moving straight forward. Look at the natural world, however, and that linear bias disappears. At every scale, from the microscopic double helix of your DNA to the sweeping arms of a galaxy, the universe's default state of motion is a spin. When we try to measure these orbits and rotations using our standard tools, like tracking distance in flat meters, the math gets tangled. A straight ruler is incredibly awkward to use on a continually curving path. Fortunately, making sense of a spinning object doesn't require learning a completely new branch of physics. You only need to learn how to translate the physics you already know. By swapping our vocabulary from straight lines to circular angles, the exact same mechanical rules that govern a car rolling down the street will map directly to a planet orbiting a star. To see how this translation works, let's put a straight-moving car side by side with a spinning fan blade. When the car drives forward, we measure its displacement as the sheer distance it travels over the ground. We track this position with the variable labeled x, measured in meters. For the fan, measuring distance in meters is messy, since the point keeps looping back on itself. Instead, we measure the angle of the turn. This is angular displacement, represented by the Greek letter theta. In physics, we measure these angles in radians, where exactly 2 pi radians makes up one complete circle. Back on the track, the rate at which the car covers those straight meters is its velocity. The fan has a direct equivalent. Angular velocity, represented by omega, is simply the rate at which the spinning object eats through those angles. If you hit the gas on the car to speed up, that's linear acceleration. Dialing the fan up to a higher setting is angular acceleration, labeled alpha. The physical nature of the movement is identical. We have simply swapped measuring distance along a straight line for measuring degrees of rotation around a center point. In linear physics, we use 3 core equations to calculate how fast an object is going or where it will end up over time. These formulas require one strict condition to work. The acceleration must be constant. The rate of speeding up or slowing down cannot fluctuate. If a spinning object has a constant angular acceleration, we can take those exact same equations and swap in our new Greek variables. Notice how all the plus signs, the equal signs, and the fractions stay exactly where they are. The mathematical logic is perfectly mirrored. Because the structure remains intact, the same algebraic steps you use to calculate how long it takes a car to brake at a red light will tell you how long it takes a computer hard drive to spin down to a complete halt. There is, however, one mechanical concept that refuses to translate in a simple one-to-one swap: mass. On a straight track, an object's mass determines its resistance to being pushed. 50 kilograms of steel is equally hard to push, whether it's forged into a tight sphere or flattened into a wide sheet. The shape doesn't matter. In a spin, shape dictates everything. We replace linear mass with a property called the moment of inertia, represented by the letter I. The moment of inertia factors in the total weight, but it also calculates exactly where that weight sits relative to the central pivot point. When you push the mass further out toward the edges, away from the center of rotation, you drastically increase the resistance. It requires significantly more energy to start or stop the spin. You see this physics in action when a figure skater enters a spin. By pulling their arms tight to their chest, they bring their body's mass as close to the central pivot point as possible. Changing their physical shape immediately lowers their moment of inertia. Because their resistance to the spin drops, their angular velocity spikes, making them spin much faster without applying any extra thrust. By learning how to translate straight lines into angles and mapping how mass distribution controls momentum, you possess the exact mathematical language required to decode the entire spinning universe. Keep your head spinning, and we'll see you in the next lesson.